Hello, everyone. My name is Michael Rebello, and today I'm going to be talking about a better way to build APIs in Swift. So to start off, I want to give a little bit of context about myself and my background. I've been building iOS apps since iOS 4, so I've been doing this a bit over 10 years. I am currently at Buff building Protobuf tools. You'll hear a little bit about that later on. And prior to Buff, I was at Lyft for about 6 years, where I worked on both the product team as well as the mobile infrastructure team. I also co-founded a startup called Path Travel, which was around for the past couple of years. And I live in San Diego, so I very much enjoy surfing and baking. And this is a photo of my wife and I in Southern California. So to start off, I want to give a little bit of context on what I'm actually going to be talking about today. So you may have heard of Protobuf or gRPC at some point. And if you heard about it from either a front-end or a mobile engineer, the sentiment you heard was probably pretty negative. You may have heard that either it's difficult to integrate into your apps, or maybe there's a poor developer experience once you actually integrate it, or maybe it's all just only about performance, and so I don't really have a good reason to care about it for my app. So none of these actually have to be true. And so today I want to explore first why we should care as iOS engineers. It turns out these technologies are not only for back-end engineers. Second, I want to do a bit of a dive into what these technologies actually are. And I'm going to share some real-world anecdotes from my past history, especially at Lyft. And then lastly, I want to talk about how we can leverage them to enhance our workflows and actually build a better experience for our users more quickly. OK, so before we dive into what these technologies are, let's go ahead and understand why we should care about them. And to do so, I want to look at the typical workflow of building a new feature. So usually when we as iOS engineers build a new feature, it requires a new API. And that API needs to be designed by someone. Many times, this is proposed by either a back-end engineer over Google Docs or Slack. I've even seen it proposed over text messages, unfortunately. After that, the team needs to come to some sort of consensus. And to be fair, sometimes these APIs kind of just get built out and thrown over the fence to us, and we don't really have much of a say. But hopefully, there's some communication that takes place among team members, again, either over Slack, Google Docs, or maybe in in-person meetings. Once the API is designed and we've actually reached consensus on it, the engineers tend to split up at this point. And we end up having the iOS and Android engineers building out the clients, and we have the back-end engineer building out the API service. And this is about the time that we start writing that wonderful boilerplate code for URL session, writing our models, making them conform to Codable, et cetera. After we've done all of this, we can finally move on and actually write the logic inside of our apps. And this is the part that we care about, right? This is the fun part. This is the UI, this is the business logic, and this is the part that we feel like we're actually paid to do. Finally, after all of this, we can ship our clients, and hopefully, at some point, we did some testing before then. Throughout this workflow, notice that we spent a significant amount of time doing chores outside of that core piece of logic. And so this would include things like repetitive boilerplate, manually testing things, or performing last-minute changes. We also spent a lot of time talking to our back-end engineers. And so the question becomes, how can we minimize the amount of time we spend doing kind of these miscellaneous things and maximize the time that we can spend focusing on the user experience? So the second issue I want to talk about is inconsistencies. And what I mean by that is inconsistencies across platforms that are usually a result of engineers deviating when they work across different stacks. And so to demonstrate, I want to give a concrete example from my time at Lyft. While I was on the product team, I often saw instances where this became a problem, and we're going to explore one of those specific examples today. So going back to our previous workflow, Lyft had something very similar to what I mentioned before, where we'd start out with a tech spec. Usually this lived in Google Docs. Once the basics were decided on, we would have 3 or 4 different engineers go out and actually handwrite these clients. So we'd basically have the same API implemented 3 to 4 different times by different engineers in Swift, Kotlin, Go. Maybe you have a front end as well, so TypeScript. And diving in a little bit deeper, I want to talk about a specific API, and let's consider canceling a ride. So the user requests a ride through the Lyft app, and they decide they want to cancel it. They no longer want to take a ride. So on iOS, we might build out a ride request, or sorry, a API request that looks something like this. So we would create a struct that conforms to Codable. Maybe we add a string field in there, which includes a cancellation reason, so the reason that the person was actually canceling the ride. Simple enough. On Android, they would do something similar. They'll create a data class with that same field. Again, fairly straightforward, right? Well, unfortunately not. It's quite easy for engineers to introduce deviations on trivial things and cause bugs. So in this case, iOS and Android only deviated by one letter. And actually, both spellings of the word cancellation are correct, depending on where you live. But this still caused a bug, and it needed to be fixed later on. And it was just a simple oversight from that tech spec. So obviously, it leads to more bugs. But depending on when those bugs are caught, this can actually lead to having to fix them on the server. So if they're caught all the way after they make it to production, someone on the back-end team is going to end up fixing the issue. And they're going to end up maintaining multiple code paths on the server for the foreseeable future, basically, until those clients are deprecated. In addition, we can actually find out that those clients don't behave the same way at runtime. So for example, let's consider the Android engineer writes a field on a response model, and that field is optional on Android. The iOS engineer just goes and writes his response model, and it turns out that that's required. If the backend engineer later on goes and decides, I'm going to change this field, he goes and reads the Android code base, turns out it's optional, removes that field or omits it at some time. If he ships that all the way to production, the iOS client will actually just explode because it can't deserialize that response. And the only way to actually understand that ahead of time is by going and reading each individual implementation of that API. And so this actually happens more often than you'd think. This is a real screenshot of some code from Lyft where a backend service was actually maintaining multiple code paths because an iOS client and an Android client both shipped completely different things, and they didn't find it until production. So at the end of the day, we're left with something like this. It's probably not our best work. It does function, maybe not necessarily that well, and it's really tough to maintain. I did not make this meme, but I very much appreciate it. OK, so how do we go about solving these problems in our applications? Well, what if we had one source of truth for our APIs? And that could be a place where we could have a canonical source of these definitions, and then we could have our clients and servers derive their implementations from that. And the way to go about doing this is with something I like to call schema-driven development. And this is a way to define APIs once using a schema, and then use them everywhere across the stack. And so we want this source of truth for our APIs to define both the shapes of our APIs. So that would include what the request looks like, what the response looks like, which fields are on those, what types the fields are, and whether those fields are required or optional. We also want it to contain information such as the behavior of our APIs. So what errors should we expect to receive? How should we retry requests? How should our APIs be rate limited? And in practice, if we have this single place where we can talk about APIs, it makes it a lot easier for engineers to effectively speak the same language and communicate a lot more effectively. So going back to our previous API workflow, let's imagine that we had that central shared schema definition. We'll get into the implementation details, but imagine that it all lives in one place. In theory, we could then use that to generate all of those clients that were being handwritten before. And not only would this eliminate all of that boilerplate code that we were writing, but that would inevitably save us a ton of time across each stack, and it would eliminate those typos and bugs that we saw earlier as well. This also means that our overall workflow that we initially saw would change. So we could take that schema definition and actually use it to collaborate more effectively. So instead of having someone propose it over Slack or text message or Google Docs, they could just submit a PR with that schema definition, and team members could actually just comment on it. We could then take that schema definition once it's checked in and just generate SDKs from it. And so again, this would allow us to skip handwriting a lot of that code. And because we've cut out some of those steps earlier on in the process, we're actually able to focus the majority of our time on the application logic. OK, so taking all of this context, how does Protobuf actually fit into this flow? Well, I want to start by introducing what Protobuf is. So Protobuf, also known as protocol buffers, is a platform-neutral language for defining and serializing APIs. And you can think about it as a programmatic way to define and document APIs across stacks in a way that makes it a lot easier for engineers to collaborate and kind of prove a common understanding. So you can imagine if we're all able to speak the same programming language, it's much easier to communicate using something that we all understand versus trying to understand a different programming language on a different platform. Protobuf was originally created by Google, and it's pretty simple to write. So we'll get into it in a bit, but it'll probably remind you quite a bit of just writing Swift structs. It also provides open source code generators for most popular languages. And this opens the door to generating that code that we talked about earlier. It does support JSON, and yes, it does support that optimized binary format. But I do want to really stress that serialization is an implementation detail. It on its own is not going to make or break our apps. The real thing that we care about here is the productivity gains that we're going to get through both collaboration as well as code generation. And that could really be game-changing for each platform. OK, so as a concrete example, let's go back to our ride cancellation API and just convert that to a Protobuf API. So the first thing we're going to do is write a request message. And so messages are very similar to Swift structs. We're going to have one field on it. So messages can have any number of fields. In this case, we're going to add a cancellation reason string field to match our previous request. Each field on a request is assigned a number. And you don't really need to worry about what this means. It's used under the hood for binary serialization. But all you need to know for now is that it just needs to be a positive and a unique number assigned to each field. Next, we're going to go ahead and define a response message. Again, this can contain any number of fields. We're just going to leave it empty for now. And finally, we're going to define a ride cancellation service. And you can think of a service as effectively a wrapper around a set of APIs. So it's just a collection of APIs. The last thing we're going to define is what we call an RPC, or remote procedure call. And you can think of this as effectively remote functions. So one you're calling on a server, for example. So instead of thinking of your API as like an HTTP post with some JSON that you're sending, try to think of it as you're just calling a function somewhere else in a library. And this is kind of that level of abstraction that you want to think about here. So we're going to define a cancel ride RPC. And it's going to take a cancel ride request and return a cancel ride response. I will say that RPCs do support streaming, but we're not going to worry about that for this example. OK, so we can actually improve that definition that we just wrote a bit. And we can do that by making the values that are acceptable explicit. And so in doing so, we can go ahead and write a Protobuf enum, which looks very, very similar to a Swift enum. And this will allow us to enforce type safety and also provide autocomplete to our client. So when we generate code, it'll be type safe. And we'll also get autocomplete for these values that we can send. Additionally, this makes it a lot easier to understand the behavior of our API in the future. So let's say we ship this API, and 6 months down the line, someone wants to understand what are clients actually sending to the server. It's a lot easier to see a typed enum that we know all of our clients and services conform to, rather than reading doc strings or reading 4 different implementations. In our request, we're going to go ahead and swap out that string field for this new enum field. OK, great. So now that we have our schema, we can actually generate code with it. And the way we do this is by using plugins. Plugins can actually be written in a variety of different languages. And as mentioned earlier, there's a bunch of them that are available out of the box. The one that we care about for our case is one called Swift Protobuf. And this is actually one that was written by Apple and is open source, maintained by them. It's written completely in Swift as well. And it's responsible for generating models. So it'll take these Protobuf messages and convert them to Swift models. And to use these plugins, we need compilers. And so the compiler effectively takes these Protobuf sources, compiles them, makes sure they're valid, and then it uses those to invoke a bunch of plugins. And so there's 2 compilers that are primarily used in the industry. The first one is called Proto-C. That's the toolchain provided by Google. And the second one is Buff. And this is actually a toolchain produced by Buff, the company I work for. And its aim is to make generation both faster and simpler. So for our Swift example, we're going to use Swift Protobuf as well as Buff to generate our code. And all we need to do is create a simple configuration file. And inside of that file, we basically specify the plugin that we actually want to use for generation. We specify the output directory, so we're just going to call it generated sources. And then finally, we can specify a few different options. In this case, we're just going to specify that the visibility of the types we're going to generate is going to be internal as opposed to private or public. Then we just call buff generate. And we're given code that looks something like this. So it's pretty easy to see how this maps back to this Protobuf, the Protobuf file we wrote earlier. So we get an enum with each of the corresponding cases. And then we get 2 Swift structs that correspond to those Protobuf messages that we saw earlier. So again, fully typed, generated from one schema. OK, so great. We have models. Now what do we do with them? How do we actually call an API? Right now, we just have models. So OK, let's take a step back and remember that Protobuf is the schema. And so that's how we define our APIs. And it's also a serialization strategy. So it's what we're sending. You can think of it as the bytes that we're sending over the wire, as well as how we're defining those. Then we have gRPC. And you can think of gRPC as the way in which we're sending those. So this is a protocol. You can think of it as how we're sending that schema and those bytes over the wire. And so gRPC is an RPC protocol that was developed by Google. It's actually just built on top of HTTP, and obviously it's built on top of Protobuf. So under the hood, it's primarily just HTTP post requests. And there's a few additional semantics, so there's some headers. If you're doing streaming, there's a little bit of extra logic under there, but it's actually quite simple under the hood. And it provides, in addition to plugins like Swift Protobuf, it provides its own set of plugins and runtime libraries. So I want to stress before moving on that gRPC itself is a protocol. It is not a library. So it's a way in which you're sending data. It is not just a library that you're importing. And to that end, when you actually put these two things together, you kind of end up with a matrix that looks something like this. So you have a set of runtime SDKs that provide the logic to power the code that's generated by their corresponding plugins. So for example, we have the Swift Protobuf SDK that powers the serialization and deserialization for the logic in the models that are generated by its corresponding plugin that's invoked by the Protobuf compiler. You also have Swift gRPC, which similarly provides the logic for actually performing that gRPC protocol, so how you send the data back and forth for the API stubs that are generated by its plugin. OK, so now that we have an understanding of how Protobuf and gRPC work together, I want to introduce an alternative to using Swift gRPC, and that's something called Connect. So Connect is an open source suite of libraries and plugins. It was built by a few engineers I work with, and it supports gRPC as well as gRPC Web, which is effectively a version of gRPC that's adjusted a little bit to work with web browsers. It also works with Connect's own protocol, which is effectively a simpler version of gRPC. I actually authored Connect Swift, which is the open source version of the Swift implementation of this. And it also, similar to Swift gRPC, provides its plugin and its own runtime library. And it's actually a lighter dependency than gRPC Swift, so it's a smaller binary size. The generated code is a lot simpler to use, as we'll see shortly. And it also generates mocks, so it'll make testing a lot easier when using this plugin. So to see how Connect fits in here, we're not going to use Swift gRPC, for example. We're going to use Connect. We're going to use Swift Protobuf for the models, and then Connect will generate the APIs for us, as well as the runtime. And you can see how the two of these fit together. OK, so going back to our configuration file, if we want to generate code for Connect, we just add another entry. So we'll add Connect Swift. We'll put it in the same generated directory that we put our models in, and we'll use the same visibility option. So when we generate, the first part of the file that we'll see is this protocol interface. And you can see that the protocol interface corresponds pretty clearly with the service that we wrote in our Protobuf definition. And then it contains one function that corresponds to the RPC that was in that definition as well. And so it accepts a cancel write request, returns a cancel write response, and it exposes a nice Swift async await interface. Further down in that same generated file, you'll get a concrete implementation. And that implementation accepts a configuration in its initializer, which we'll get into shortly, that basically just tells it how you actually want to perform that request. So for example, if you want to use JSON, or if you want to use Protobuf binary serialization under the hood. And then you see the implementation of that cancel ride function. And it's actually very straightforward. It just specifies the path, which is per the gRPC spec. It can determine the path. And then you can specify the requests and the headers, and then await that response. OK, so we're ready to use these generated APIs in our app. And to do so, we're going to start by importing Connect and importing Swift Protobuf. The next thing we're going to do is we're actually going to configure it. So this is a one-time configuration, and you'll use it across your app. So very similarly to how you use URL session across your app, you probably share one instance. You'll do something very similar here. And so we're going to configure it with, one, the HTTP client to use. We are actually going to use URL session. It's a small wrapper around it, but we're going to use URL session. We specify the host. So a lot of times this would be staging or production. In this case, we're just going to specify a demo. We specify the network protocol. And then we're going to specify the codec to use. So whether we want to use JSON to serialize our models or that binary Protobuf serialization. Lastly, we're going to go ahead and create our client using this configuration. And then most importantly, we're actually going to call that function. And so I really want to stress here that it's just one line of code to actually perform this API call. So we're taking a typed generated request, sending that to a generated function, which is also typed. So we're just awaiting client.cancelRide, sending that request, and then awaiting the typed response. So there's no creating dictionaries here. There's no passing around JSON models. There's no handwriting Codable models. Everything is just generated for you, and you can just call that API with one line of code. And to that extent, it's actually very easy to change the implementation details under the hood. So as I mentioned earlier, I want to think about this as not performing HTTP APIs, but you're just calling a function somewhere else. And to that end, you can actually completely change how the data is sent over the wire just by making a couple lines of code changes. So here, for example, we're going to change the network protocol. And then we do actually have to change the HTTP client if you're using gRPC. And that's because of an implementation detail with gRPC where it requires trailers support, which are basically headers that come after the body of a request. And unfortunately, URL session does not support trailers. So we have to actually use Swift NIO for that. But it's really important that just with these 3 lines of code changes, you can change how the APIs actually communicate under the hood, but everything else stays the same. So all of the generated APIs stay the same. The interface is completely abstracted, so none of your application code changes, and that generated code doesn't change at all. OK, so as I mentioned earlier, Connect Swift also supports mocks. So these conform to the same protocols that were generated at the top of the Connect file. They're super easy to configure and generate. So if we want to do that, we just add one new entry to our configuration. This time, we're going to put it in a different directory. We're going to put it in generated mocks instead of our sources directory. And then we're given a file like this. So it's pretty straightforward. You're given a subclassable mock. And again, like I mentioned earlier, it conforms to that same client interface. You're given a closure that is customizable, so you can actually validate the request and specify a response to set by default. And then you're given the implementation of that cancel ride function, which effectively calls that closure. So when we actually want to test with our generated mocks, it's really easy to go ahead and create a test client and inject that into a view model, for example. So we can actually take that, validate the fields on the request. So again, instead of validating fields on a dictionary, you're creating a dictionary and sending that through. We can just validate that a property on an actual type is there. We can also simulate a response. Again, no dictionaries, all typed. You just create a Swift model and return it. And then you can validate the business logic inside of your view model. Additionally, this also makes it really easy to do UI testing. So instead of importing JSON files or passing stuff around, again, you can just mock it out, and it's all type safe. Importantly, it's also guaranteed that the responses and requests you write will correspond to what's on the server, because the server is using that same generated interface. OK, so now that we've done a brief crash course on Protobuf and gRPC, what are some of the real-world results that we can expect if we were to adopt them? So I want to talk about this from the perspective of my experience at Lyft, where on the infrastructure team, we supported about 120+ mobile engineers. And during my time there, we started with all of our existing REST JSON APIs, which was like 200 to 300 of them. And over the course of about a year and a half, we migrated all of them over to using generated Protobuf APIs. And so when we did that, Protobuf became our single source of truth for all of our APIs. So every single request that was sent from our iOS or our Android app was defined in Protobuf, and that made it really easy for engineers to understand how things worked. It also made it really easy for engineers to collaborate on API schemas. So a lot of the development workflow for APIs actually moved to the left in the development workflow. And so mobile engineers ended up having more of a say in what those APIs looked like, because you'd have a backend engineer submit a PR with that schema definition, and then the mobile engineers would be able to comment or even propose their own. And so we moved that collaboration piece into the PR, and people felt a lot more free to actually contribute. Thirdly, we obviously eliminated a ton of handwritten API boilerplate, deleted tens of thousands of lines of code, and removed a lot of associated bugs. So we ran into inconsistencies while we were migrating, and found that, of course, there were some of those bugs that were a result of deviating between platforms. We also prevented accidentally breaking clients with bad server code changes. So if in the past we had some Python code or some Go code where the engineer could just kind of change it and ship a change, and hopefully it didn't break a client, when they moved to schema-driven development, that meant that because they're using those schemas for their requests and their responses, someone actually had to go submit a schema change, and someone had to approve it. So it kind of added another barrier to breaking those APIs. Additionally, our code testing coverage went way up because we were able to generate mocks, and it made it much, much easier for engineers to actually write tests. People started doing UI tests as well, so that was really great to see. The network implementation details were fully abstracted, so engineers no longer needed to manually invoke an HTTP client or pass around a URL session instance. They just called these generated APIs, and the infrastructure team was able to manage kind of how the data was sent underneath all of that. Lastly, we were able to get a better understanding of how these backend systems work. So if you wanted to know how a specific API actually functions or how it's implemented on the server, it's really easy to do just by knowing the request model name or the RPC name. You just do a code search on GitHub, and you can find all of the clients using it, as well as the actual implementation on the backend. So there's a lot more you can do with Protobuf, which I'd like to touch on briefly. And part of my job at Buff is to work on tools for the Protobuf ecosystem, and our goal is to do that so you don't have to. And the one that I want to call out that's super relevant to us here at a Swift conference is generated SDKs. And so Buff provides a schema registry, which acts as a centralized location for storing your Protobuf schemas. And effectively, the way that usually works is you'll submit a PR with your schemas, you'll merge it to main, and then usually a CI job will pick it up and just push it to this registry, and that's about it. But because it's in a centralized registry, we can actually generate SDKs for you. And so effectively, your workflow becomes you submit a PR, you merge it to main, it gets pushed up to this registry, and then you're given a Swift SDK that you can integrate directly into your project. So you're no longer handwriting APIs, no longer handwriting models. You're not even manually generating code anymore. You just push something up, and then you're given a package. And these packages are compatible both with Xcode and Swift Package Manager. And they're available the same way you'd pull in any other SDK from GitHub. So you just put in a URL, tag the version, and you're good to go. And it's actually completely free, so I'd encourage you to check it out. The other thing I want to touch on is preventing breaking changes. So most of us have probably experienced a breaking API change before. This usually causes an outage and is probably a result of someone either deleting a field in a response or changing the type of a field or otherwise modifying it in a way that clients don't support. And we can actually prevent this by using Protobuf. So we have a tool that we can use which prevents these changes from going out. And effectively, the way this runs is we compare the diff in your PR when you're proposing a schema to what's on main. And if it detects a breaking change, such as someone deleting a field or renaming it, we can just fail CI, and that change will never make it to production. So it saves a huge amount of headache, especially for client engineers, because no one can just mistakenly change an API and break production clients. The last thing I want to mention is that if you're new to gRPC, you probably have a bunch of existing REST JSON APIs. And in order to have consistency across your APIs in your code base, you probably want a way to support those APIs. And so we're planning on adding support. Again, this is an open source repository. We're planning on adding support for REST JSON HTTP APIs to connect Swift. And this will allow you to use those same libraries for your existing APIs without requiring your backend to migrate to using gRPC or to use any of this technology. And so this will be able to be done with just a couple of annotations. So for example, you can specify that this RPC should, instead of using one of those protocols, just be a post request at the specified path. And then we'll send the entire request, the request body using the request message that was specified. So again, all of that can be done with 0 changes to your actual implementation. So there's a swath of ways that Protobuf can be used. Just to touch on a few of them, so one other one is enforcing data field validation. So this might be, for example, validating phone numbers or validating email addresses on a request that makes it to your server. This can all be specified by just adding an option on your request message. Second, you can actually generate your own code. So this could be generating extensions, this could be generating additional types, it could be generating documentation or metadata. And you can do this just by writing another plugin in Swift that's invoked by that compiler. And one of the things we did at Lyft while we were here is we actually automated polling. So many of us write polling for our APIs to routinely fetch data. And one of the things that we added was effectively just an annotation. So one additional option that we specified on each API that specified a polling rate. And then we would just generate a streaming function that under the hood handled polling. It would handle deduplicating requests. So again, it made it really easy for engineers to do the right thing when actually polling APIs. Lastly, Buff is also working on some ways to support Protobuf outside of APIs. So that would be things like structuring events or structuring your actual database. And honestly, this list keeps going on. There's a bunch of different ways this is applicable. I'm really excited about the API speech because that's the way I've seen it have a big impact on my development workflow. So to that end, I would be really happy to discuss how you can use Protobuf in your apps. I'll be around after this if you want to chat. And I hope this provided an interesting alternative to writing APIs the quote-unquote old-fashioned way. So if you'd like to explore this for yourself, you can check out the open source repository, this QR code, or connectrpc.com. And thank you very much for your time.